Today we're going to have some extra practice with those integrals for our arc functions, as well as taking a look at some slope fields, which we've seen before. So slope fields aren't in the video, but of course, as always, if you do have questions on them, just reach out to me. Starting off with a differential equation. As a reminder, when we solve differential equations, we have got to separate those variables. So I'm going to multiply both sides by dx, and then I'm going to look for a pattern to see how I can integrate my function. All right, I notice that there is a square root in the denominator, so that narrows it down to the arcsine and the arcsecant functions. There is no variable being multiplied outside the square root, so I do know I'm working with the arcsine function. I've got my a squared right here, so a is 2. And of course, I've got my x squared function here, so x is x. Integrating both sides, I get y equals the arcsine of x over a, or x over 2, plus c. We were given this point. If we put 0 into our function, so 0 is the x value, we get pi out of our function. So we're going to sub those in to solve for c. Again, y was pi, and x was 0. So we're thinking about the arcsine of 0. What angle gives us a sine value of 0? Hopefully you came up with 0. So we get pi equals c. Rewriting our integral with pi instead of c, we get y equals the arcsine of x over 2 plus pi. All right, we're going to be revisiting our natural exponential function on this one. Notice our function is y equals 4 e to the x all over 1 plus e to the 2x. And we want to determine the area between that function, the vertical lines 0 and 1/2, and the x-axis, or the horizontal line y equals 0. So basically what this is asking us is to integrate the function. Integrals give us that area under the curve. So I'm going to set this up, looking for the integral of, I'm going to take that 4 in the numerator and pull that out front. That is just a coefficient. We can pull those out front so that we don't have to worry about them as we integrate. And I want to look at that denominator, that e to the 2x. As a reminder, with our power rules, if you take a power raised to a power, you multiply the exponents. So e to the 2x is the same thing as e to the x squared. The reason I did that was so that I could recognize this pattern. It is one of our arc-trig functions. There's no square root, so it's not arcsine or arcsecant. We have a squared plus u squared, and we have the derivative of u in the numerator. So if you're one who wants to look for patterns, we found the pattern. If you're one that has a little bit harder time with the patterns, then we are going to say let u equal e to the x. The derivative of u is e to the x dx. So this is our numerator. All of that's going to be replaced with du, and we're going to put that u in the denominator for e to the x. Still have that coefficient. We've got du in the numerator, or you can put a 1 there with that du on the outside like I normally do, and 1 plus u squared in the denominator. This is our arctan pattern as we are integrating. So taking the integral, I'm going to get that 4 as a coefficient. Our arctan integral is 1 over a, well, a is 1, so that makes it kind of helpful for us, times the arctan of u over a. Again, a is 1. So I just realized that I forgot to put the bounds on our integral in the first place. So instead of re-recording all of the work for this problem, which I'm really not excited about, I'm just going to go back to our blue integral. We were looking for the area under the curve between 0 and 1/2. Now, since I let u, the bounds would change, but I'm going to go ahead because I did this with recognize the pattern. So I did evaluate this with our e to the x function instead of the u function. So I'm going to go ahead and rewrite this back in terms of e to the x, and then we'll go ahead and sub in. All right, so 4 times 1, of course, gives us 4, and then we have arctan of e to the x over 1, which of course is just e to the x. I think I write too fast for my tablet. All right, and then 0 and 1/2 were our bounds. Summing those in, we get 4 times the arctan of e to the 1/2, or the square root of e, minus 4 times the arctan of e to the 0. Now, since we won't be able to simplify this first one exactly, we could either, to give an exact answer, we would leave this as 4 times the arctan of e to the 1/2. And then e to the 0 is 1. We can exactly find the arctan of 1, which angle gives us a tangent value of 1. Hopefully you came up with pi over 4. And then our 4's would cancel, so an exact value would be 4 times the arctan of e to the 1/2 minus pi. Or a decimal approximation would be 0.9608. All right, so today is day 2 of practicing our integrals with our arc-trig functions. So once again, gentle reminder, use those Quizlets to help you get those memorized and recognize those patterns, because you do have a test coming up pretty quick.